Put a short plank across a narrow gap and it feels almost boring. Step onto it and it holds. Now move the supports farther apart. The same plank bends more. Stretch the gap farther still, and eventually it cracks. That simple problem sits underneath every bridge ever built. Ancient builders had no steel girders, hydraulic cranes, or computer models. So how did they carry people, carts, roads, and sometimes entire armies across rivers that were far wider than any useful piece of timber? The simplest bridge is also the easiest one to understand. A beam. A log, a timber, or a flat slab rests on two supports and carries weight across the gap. For short distances, it works beautifully. The problem is bending. The top of the beam gets compressed while the underside is pulled apart. Make the span longer or the load heavier and those forces grow. Wood can also rot, burn, or be torn away by floods. A wider crossing demanded more than simply finding a bigger log. Stone looks like the obvious upgrade because it can carry enormous weight. But stone has an awkward weakness. Press down on it and it performs extremely well. Bend it or pull it apart and it can crack surprisingly quickly. So replacing wood with a flat stone beam does not magically solve the problem. Ancient builders needed a way to make stone work mostly under compression, where it was strongest. The breakthrough was not just choosing a tougher material. It was arranging that material so the forces moved through it differently. That is where curved structures become powerful. In a true masonry arch, wedge-shaped stones press against one another as weight pushes down from above. Instead of forcing one long slab to bend, the curve directs much of that load through compression toward the supports on both sides. The important part is not a magical center stone. It is the entire geometry of the arch and the solid supports resisting its outward thrust. Ancient builders learned to control that behavior through construction practice long before engineers described it with modern equations. Bronze Age Greece gives us an earlier and slightly different solution. The bridge at Kazarma, often called the Archidiko Bridge, was built from massive limestone blocks fitted without mortar. It is not a Roman-style true arch. Its opening is formed by corbelling, with successive stones projecting inward until the gap is covered. That distinction matters. It shows there was no single moment when bridge engineering suddenly appeared complete. Builders were experimenting with heavy stone and geometry in several ways, adapting what they knew to roads, terrain, and available material. But the arch you see above the water is only half the problem. A beautiful stone span is useless if the supports underneath it sink, tilt, or get washed out. The hardest part of many river bridges is hidden below the surface. Before anyone can stack masonry high into the air, they need something stable at the bottom. And that creates a much stranger construction problem. How do you build a solid foundation in a place where water is flowing, the riverbed may be soft, and workers cannot simply stand there and dig? Roman sources describe one answer: temporarily turn part of the river into a work site. Builders could drive wooden piles into the riverbed to form an enclosure, seal gaps with materials such as clay, then remove water from inside using pumps or lifting devices. This type of temporary enclosure is what we now call a cofferdam. Once the water level inside was lowered, workers could excavate toward firmer ground and construct a foundation in relative dryness. The river kept flowing outside while a small patch inside became buildable ground. Sometimes the bottom itself was the bigger problem. If firm rock was close to the surface, builders could work toward it. If the riverbed was deep mud or weak sediment, piles offered another option. Timber posts could be driven downward until they reached more resistant material or created a dense foundation capable of distributing load. There was no universal ancient recipe for every river. The important idea was simpler. The bridge could not just sit on whatever happened to be beneath the water. Its load had to reach something capable of carrying it. Even a strong foundation still had to survive the river. Flowing water does more than push against a pier. It can accelerate around the structure and remove sediment from the riverbed, slowly digging around the foundation. Engineers call this scour. Builders learned to shape some bridge piers with pointed upstream ends that divided the current instead of meeting it as a flat wall. The bridge therefore had two completely different jobs at once: carry weight from above and survive moving water below. Ignoring either one could eventually bring the whole structure down. Once the piers were ready, there was another paradox. A finished stone arch can support itself, but an unfinished arch cannot. During construction, workers needed a temporary wooden framework called centering. It created the curve that the masonry would eventually follow. Stones were placed across that frame until the arch was complete and capable of carrying its own load. Only then could the timber support be removed. For a while, The permanent stone bridge depended entirely on a temporary wooden bridge underneath it. The finished structure hid the scaffolding that made it possible. And those stones did not float into position. Ancient builders had machines, just not engines. Levers could pry heavy blocks upward a little at a time. Ramps traded lifting height for distance. Hoists and pulley systems multiplied human or animal effort. Wooden cranes could raise cut masonry far above the ground. The technology looks simple compared with modern equipment, but the physics is the same. The key advantage came from mechanical leverage. Instead of asking one person to become impossibly strong, builders arranged ropes, beams, wheels, and teams so ordinary force could move extraordinary weight. Lifting the stone was only useful if it landed in the right place. Bridge construction demanded alignment across spaces workers could not simply measure by walking straight through them. Ancient surveyors relied on sight lines, plumb lines, water levels, ropes, repeated measurements, and geometric methods to establish height and direction. Small mistakes could become large ones after dozens of courses of masonry. Precision, therefore, came from repetition and skilled observation rather than electronics. Two sides of a project had to follow the same intended line long before the final stones met above the water. Rome did not invent every part of bridge building, but Roman engineers became exceptionally good at combining techniques into a repeatable system. Surveying, foundations, masonry, timber centering, roads, organized labor, and material supply could all become parts of one infrastructure project. That mattered because a bridge was rarely useful by itself. It had to connect to roads, settlements, military routes, and supply networks. Once those pieces worked together, a bridge stopped being a clever object over water. It became part of a larger machine for moving people, messages, animals, goods, and armies. Roman builders also had access to hydraulic construction materials that were especially useful around water. Mixtures containing lime and volcanic material could harden in conditions that ordinary air-curing mortars handled poorly. Modern research has also found that some Roman concrete formulations contained reactive lime-rich particles capable of helping seal small cracks when water entered them. That does not mean every Roman bridge automatically repaired itself. But it does show how material chemistry could add another layer of durability. Geometry carried the forces, while the material helped the structure survive the environment. Stone arches are powerful, but they need supports. Now imagine a deep canyon where the opposite cliff is far away, and there is no practical place to build a pier in the middle. Suddenly the logic that worked for a river becomes useless. You need a bridge that can cross open space while almost everything underneath remains empty. That changes the force you want to control. Instead of making stone push against stone in compression, builders can use long fibers that are pulled tight. The problem moves from compression to tension. A suspension bridge works by hanging the crossing from cables anchored at both sides. The weight of people and the deck pulls on those cables, and the tension travels toward strong anchor points in the surrounding ground or rock. In the simplest comparison, an arch pushes while a suspension bridge pulls. That difference makes suspension especially useful where building intermediate supports would be difficult or impossible. The materials can look surprisingly humble. If enough strong fibers are twisted and braided together, plant material can become a structural cable capable of carrying people across enormous gaps. The Quesuachaca Bridge in the Andes shows this principle as a living tradition. Local communities gather grass, prepare the fibers, twist them into cords, braid those cords into larger ropes, and combine the ropes into major bridge cables. The cables are anchored on opposite sides of a canyon and support the crossing between them. Nothing about the material looks permanent. That is exactly the point. The bridge does not survive because grass lasts for centuries. It survives because the knowledge of how to turn grass into a bridge continues to be practiced. Quesuachaca is traditionally renewed on a regular cycle, with communities rebuilding the bridge using inherited techniques. That gives us a very different definition of durability. A stone bridge may endure because its material and geometry remain stable after the builders leave. A fiber bridge can endure as a crossing because people keep replacing the material before it fails. In one case, continuity sits inside stone. In the other, continuity sits inside a community. The structure is temporary, but the engineering tradition can last far longer than any individual rope used to make it. Ancient Chinese bridge builders developed their own sophisticated answers to the same basic forces. The Zhaozhou Bridge, completed in the early 7th century, uses a shallow segmental stone arch with additional openings in the spandrels. Those openings reduce unnecessary masonry and allow more water through during floods. It is a reminder that bridge engineering was never one simple line from one civilization to another. Different builders could manipulate weight, compression, flow, and material in distinctive ways, because the environment presented different problems and local traditions offered different tools for solving them. That is why there was never one best ancient bridge. A shallow stream may need little more than a short beam. A broad river might reward piers and arches. Soft sediment changes the foundation problem. Strong floods change the shape of supports. A deep canyon makes suspension attractive because the center can remain empty. Good engineering starts by asking what the obstacle is actually doing. Ancient builders were not choosing between a list of universal bridge types. They were matching material, geometry, labor, and terrain to a specific physical problem in front of them. None of those solutions could be built by one clever person with a rope and a chisel. A serious bridge required quarrying stone, cutting timber, preparing fibers, moving materials, surveying the site, feeding workers, building temporary structures, and coordinating specialists who understood different parts of the job. Carpenters, masons, laborers, surveyors, rope makers, transport crews, and organizers all became part of the same system. The invisible machine behind many ancient bridges was not a piece of equipment. It was the ability to organize large amounts of skilled human effort toward one shared structure. Failure was part of that knowledge. Timber rotted.
Beams bent.
Foundations shifted. Floods removed soil. Masonry cracked when supports moved. Builders did not need a modern engineering textbook to notice those patterns. If one method repeatedly failed under certain conditions, the next generation could change the shape, material, foundation, or construction sequence. We should be careful not to invent specific experiments that archaeology cannot show us. But accumulated craft knowledge clearly mattered. Every successful bridge represented not only what builders knew worked, but also generations of practical lessons about what did not. Modern engineers can calculate many structural forces with equations and software before construction begins. Ancient craftspeople worked differently. Their knowledge lived in measurements, proportions, tools, routines, and experience with actual materials. A skilled mason knew how a particular stone fractured. A carpenter understood how timber behaved under load. A builder working near rivers learned which ground stayed firm and which washed away. That was not formal modern science, but it was not ignorance either. The laws of physics were the same. The difference was how people learned to recognize and use them. Solving the bridge itself changed much more than transportation. A reliable crossing could turn a seasonal obstacle into a continuous route. People, animals, carts, traders, messengers, and soldiers could move without depending on a ford, ferry, or favorable water level. Roads that once stopped at a river could continue on the other side. A bridge, therefore, changed the practical geography of a place. The river was still there, but its ability to interrupt movement had been reduced. Engineering had not removed the landscape. It had changed what humans were able to do within it. So how did ancient people build bridges without modern machines? They did not use one lost technology, and they were not secretly building with modern equipment. They used simple machines, careful geometry, local materials, stable foundations, compression where stone worked best, tension where fibers worked best, precise craft, and organized labor. Most importantly, they inherited knowledge accumulated through repeated building and correction. The impressive part was never that ancient people somehow ignored physics. It was that, with limited tools, they learned how to make physics work for them.